We're going to talk about something called an annuity here, and this actually is a more common type of spending or paying off a loan than just using a one-time deposit and then letting it sit. So most often you're going to make regular payments, like maybe every month you put away $100 for your saving for retirement, or perhaps every week you make a payment for your mortgage or your house. That's an annuity. So here's an example of an annuity. Peter saves $400 per month at the end of each month for 6 months in an account that pays 9% per annum compounded monthly. How much will he have saved at the end of 6 months? What we're going to do here is break this into smaller pieces, and then we're going to talk about an actual formula that will help you calculate this much more quickly. So first of all, I'm going to develop what's called a timeline here. So it literally is a line where this is going to represent the month, and this will represent underneath the payment amount. So month 0, so at month 0 we haven't made any payments, but by the end of the month 1 we are making a payment of $400, and at the end of month 2 we're paying another $400 into this account, and so on here for 6 months. So we've got 4 payments of 400, now 5 and 6. So 400 goes here and 400 goes here. So I really didn't need to make that line quite that long. Look at me go there. I was able to erase that without deleting the whole line, which I have been able to do in the past. All right, so I'm going to actually work backwards here. At the end of 6 months, this $400 that was deposited at the end of that 6 months, that is only worth $400 because it went in and has no time to earn any interest. However, the second last payment, it has a chance to earn 1 month's worth of interest. And remember to calculate your amount that an investment was worth using compound interest. It's this formula here, A equals P 1 plus I to the n. Now, it's compounding every month, so this $400 payment here, its amount starts out at $400, but it has 1 compounding period's worth of interest to add on to that. Now, the 9% per annum, it's compounded monthly, so our I value is 0.09 divided by 12, which is 0.0075. Hopefully you can read that. It's a little squishy. So 0.007, that's a 7 and a 5. So that has 1 month's worth of interest. That's 1 compounding period there. So that's going to actually be worth $406.02 if you put that in your calculator. So it is actually earning $6.02 in interest for having sat there for 1 month. This $400 payment actually gets to have 2 months worth of interest added onto it. So we're going to do this calculation again. I'm going to just add those values together, the 1 plus 0.0075. That has 2 times that it compounds. That amount we can calculate as well to figure out what it is worth, and so on. We're going to do that for each one of these $400 payments. We're going to get the amount that it is worth at the end of 6 months, and then the total amount we have will be the sum of those values. So take some time and fill in the values for each of those and then add them together. And I just realized I had made a mistake here. That wasn't 406.02. That's what the second one was equal to. This one should just be $403 there. $403. Okay, so by putting $400 per month in at the end of each month for 6 months into this account, he ends up with $2,445.46. So this is an example of an annuity. If I wanted to get the total amount of interest he actually earned on his investment, he made $400 payments, and he made 6 of them. 1, 2, 3, 4, 5, 6. That is $2,400. The difference, the amount of interest he made, would be the difference between the amount of his investment So $2,445.46. Now we might have a bit of a rounding error because we've rounded every single one of these up, I think, when we rounded them. So just be aware of that, that when we do a different calculation for this, we might be out by like a cent or so. All right, so in total, he's earned over 6 months, he's earned $45.46 without really doing anything extra there except making sure he puts the money away. So an annuity is just a series of equal payments or deposits made over regular intervals. So car payments, mortgage payments, retirement savings plans, when you're putting money away to save for something, those are examples of annuities. All right, so our annuity is a series of equal payments. So in this case, Peter was making every payment of $400, so they were all equal in amount, or deposit, you could say, and it's made every single month. So that's the regular interval. A simple annuity is a special type of annuity where the payments occur at the same rate as the compounding occurs. For example, if you're making monthly payments, the interest is compounded monthly. Or if you're making annual payments, your interest is compounding annually. That's what a simple annuity is. Mortgages in Canada are not simple annuities usually because you're usually making weekly payments or bi-weekly payments or monthly payments, but in Canada, our mortgage rates are compounded semi-annually. So it's a little bit different, and there are apps or applications on our websites that will help us with those. An ordinary annuity means that our payments are made at the end of each payment period. So notice Peter didn't make his first deposit until the end of the first month. So that has to be true for this formula to work that I'm going to show you here now. Let's see if I can move this. So if we have this case where we have a simple ordinary annuity, then we can use this formula down below here. We have the future value. So FV just stands for future value. It's like the A in our compound interest formula. So FV for future value. The R represents how much your regular payment is worth. So this is the amount of your regular payment. So in Peter's case here, we have a $400 payment. So that is the value of our R. And then you'll notice I appears twice. I is here and I is here, and it represents the exact same amount. It's just in two different places in the equation. And that I is exactly as we have defined it before. It's your interest rate per compounding period. And then N is just the number of times that it compounds, just like it was before with our compound interest formula. So let's look at the example with Peter here. We know that his regular payment was $400. So we could actually use this formula to calculate it without having to do all the pieces that we did up above or on the previous slide that I had. So $400 is the regular payment. We're going to have a bracket 1 plus I, which was 0.0075. And then it was compounding 6 times. Overall, we had 6 compounding periods. So we need an exponent of, oh dear, I'm having trouble writing right there for some reason. Can I slide it down? Maybe, yep. There we go, 6. Whew. And then minus 1, close that bracket. And that calculation, so we do all of that, has to get divided by 0.0075. So try that on your calculator. I'm going to do what's inside the brackets first. So for me, I'm going to type in 1.0075 to the exponent of 6. Get that answer. I'm going to subtract 1 off of that. Then times it by 400. Get that answer. And then divide by 0.0075. And I get, oh, look at that, $2,445.45. So that looks pretty good. Again, there might be a little bit of a rounding error just because this will take everything into consideration, whereas we rounded a bunch of answers up. So we were out by a cent there. Okay, so let's try using this formula here. Leslie wants to have $10,000 saved 2 years from now. So time frame 2 years from now. So this looks like the future goal here that we want as a down payment on a new car. She figures she can afford to save this much every 2 weeks. and can invest it in an account that pays 4.5% per annum compounded every second week. So these correspond to each other, that they match. Will she have enough saved by that time? All right, by how much is she off her target amount? So she's hoping for $10,000, but the second part here, by how much is she off? She might not have enough based on this. So let's figure things out here. Her regular payment, we can figure out the future value. Her regular payment is $175. We can figure out the I value. So R is $175. The I is 0.045, and it's every second week. Now remember, there are 52 weeks in a year, so if we're going every other week, we're going to divide by 26 there. So 0.045 divided by 26. I'm going to use all the digits on my calculator. And then N, we have 2 years. 2 years every 2 weeks. So 26 payments, and that's 2 times 2 years of that, which is going to be 52 payments overall. So this will be a 52, and then we have our minus 1, close the bracket, and we're going to divide that by the answer we get when we do 0.045 divided by 26. So lots of stuff to put in our calculator here, but again, I'm going to do this all in one big calculation to avoid rounding errors. So 0.045 divided by 26. I'm going to add 1 to that, and then I'm going to go to the exponent of 52 and subtract 1 from that. Multiply that by 175, and then divide it by, and I'm going to put brackets around this, divide by bracket 0.045 divided by 26, close that bracket. That gives me $9,513.46. So she's shy of her target. To get how much she's short by, we'll just subtract that amount from the $10,000 goal. So she's short by $486.54. Okay, will she have enough saved by that time? Nope, she's off by this much here. So she'll have to save a little bit longer to make her goal of $10,000.